Hello, everyone, and welcome to the presentation of my PhD thesis. The title of my thesis is Autonomous Low-Cost Data Capture and Inference with Incomplete Data for Indoor Construction Environments. As you might know, construction is one of the world's largest industries. Despite that, the industry still faces significant efficiency challenges. For example, correcting work that has already been done is common in construction, often simply because the as-built does not match the design. So implementing effective construction control processes is crucial to address and improve this issue. Manual reality versus design comparisons could be quite complex and costly at a large scale. The reality capture cycle is one systematic approach to automate these comparisons. In this framework, we collect on-site data, images or 3D point clouds, for example. We process them to extract useful information, which is then documented or modeled in BIM and is used for further informed decision-making. The key to this process is on-site data, the core of this thesis. My thesis addresses two major challenges related to on-site construction data. Because of the clutter and the dynamic nature of indoor job sites, frequent data capture becomes a challenging task. In the first part of this thesis, the focus is going to be on enabling low-cost autonomous indoor data capture with a particular emphasis on localization in indoor construction environments. But data capture is not the goal here, right? We have to be able to extract relevant information from the data. The thing is, even with an ideal data capture solution, it's kind of impractical to guarantee complete on-site data because of noise and occlusions on site. So the second part of this thesis focuses on inference with incomplete data. Let's start with data capture. Well, autonomous robots can be very helpful to carry sensors around for us to automate on-site data capture. What you can see here are instances of robotic data capture solutions mainly used in outdoor settings. In practice, however, we don't see as many options for indoor construction. Let's focus on visual data. On-site images are still mainly captured manually indoors. This is partly because the existing robotic solutions are expensive, and mainly because autonomous navigation is actually very hard in indoor construction. So we asked ourselves, how could we enable low-cost aerial robots, or UAVs, to autonomously collect images in indoor construction settings? I said autonomous navigation on indoor construction sites is highly challenging. One major challenge is the localization of the robot, which is the key enabler for autonomy, and therefore the focus of this thesis. Like any other indoor scenarios, GPS just doesn't work. Wave-based methods like ultra-wideband are hard to use due to wave interference with construction materials. Low-textured and repetitive areas like white walls, which are very common in indoor construction, will break feature-based methods such as Visual SLAM. On the other hand, for the BIM, and practices such as regular indoor layout surveying can benefit indoor localization. Fiducial markers like April tags can be very helpful. They are inexpensive and long-lasting features, and once distributed, they can be surveyed too as indoor surveying is being performed. What this thesis proposes is a tag-based indoor localization method that estimates the full pose of a UAV or really any other devices with a camera and an IMU. Given known tag locations and sizes, this method fuses odometry data from IMU as inputs with tag readings from camera as measurements. Let's see this simplified example to review how this fusion works. Let's say we have a little ground robot that wants to estimate its one-dimensional position along the x-axis. It has some ideas about its initial state, but its belief is uncertain. So we represent its position and the associated uncertainty with a normal distribution with a mean and a standard deviation. Now the robot moves, and using its inputs through IMU or wheel odometer, it predicts where it may end up being based on a motion model. But this prediction is not perfect. To correct that, it measures its distance to the wall in front of it. This is where the measurement says the robot is through its measurement model. Now, given the uncertainties associated with each piece of information, we fuse the two to get a better estimate of the robot's state. It goes forward and keeps updating its belief through prediction and correction steps. Let's get back to our problem. On the right, we can see the vehicle's rigid body and its onboard camera. We can see tag J and our fixed global reference frame. The vehicle pose that we want to estimate is a 4x4 transformation matrix in SE3 or spatial Euclidean group in 3D. The inputs to our system include the initial pose of the vehicle as well as the rotational and translational velocities. The measurements are the pixel values of the corners of the detected tags. For instance, if we see tag J at time K, we get 4 pixel coordinates, 1 for each corner. Finally, we fuse these two sources of information using an extended Kalman filter. For now, we assume that the tag poses are perfectly known. Because our motion and measurement models are nonlinear, we need to linearize them to use Kalman filter. That's where the term extended comes from. And for that, we need to find the derivatives, or to be precise, Jacobians of the motion and measurement models with respect to the state. But our state, posed in 3D space, lives on a curved yet smooth space or surface that is called a manifold. So we have to follow certain mathematical rules to handle these derivations. But at the end of the day, we have the same steps to follow as we saw before. Predict the state, calculate how much you should trust your measurements, and correct your belief based on the measurements. In this video, you'll see one of the lab experiments demonstrating the performance of our estimator. Tag poses were accurately estimated using overhead motion capture cameras before the test began. On the right side of the screen, there is a visualization of the workspace on the XY plane, the tag configuration, and the X and Y estimates. 3 moving dots are visible. Red corresponds to the dead reckoning estimates, meaning no tag measurements incorporated. Blue represent the tag-based estimates, and green corresponds to the ground truth. To enhance visibility, the complete ground truth trajectory has been displayed as dashed lines. You can also see a 3 sigma uncertainty envelope represented as an ellipse. The size of the ellipse corresponds to the level of uncertainty. In our multiple experiments, in simulation, and laboratory settings, we achieved a root mean square error of between 2 to 5 centimeters in 3D position estimation. But we don't have overhead cameras on site, right? And there might be errors in tag pose determination. This error can be represented as uncertainty in the tag pose. And our formulation beautifully allows us to incorporate this in our estimation problem. This will affect the correction step through Kalman gain, and particularly the process noise in the measurement model as it changes with the vehicle's pose. I present here one experiment where we expose the tag poses with extremely high uncertainty and compare the robustness of our method with and without modeling the uncertainty. Blue is without and black is with. As you can see on the left, where the vertical axis shows the error in X, Y, and Z estimates, without uncertainty modeling, the estimates diverge in high uncertainty regimes. But when we simply acknowledge the fact that tag poses are uncertain, we can be robust against those divergences. But how many tags do we need to support localization? Which sizes should we use? Where do we need to put the tags to minimize manual installations as construction progresses? How we should make sure that the localization quality is good enough? The quality of localization can be quantified using the Fisher information matrix. It specifies how certain we are in our estimates. Obviously, this will change as the vehicle moves around, for example, as it moves vertically, as you can see on the image. But we even have more challenges in construction. As construction progresses, the layout changes, and therefore, the options for installing tag will change. Some tags might be occluded, and some might be damaged. Also, the locations that the UAV has to visit to capture data will change. So the regions of interest, the hashed boxes in this GIF that you can see, will change. We propose a perception-aware genetic algorithm-based tag placement planner. First thing first, we discretize everything. We take different snapshots of the project according to its inspection plan and its 4D BIM, 3D model plus schedule. We slice each snapshot along the z-axis. We convert everything to 2D polygons. And finally, we find a finite number of tag location options on allowed surfaces and discretize vehicle poses in the regions of interest. To use genetic algorithm, there are two requirements. The first requirement is defining feasible solutions as essentially an array of integers. In a project with m phases, we find the union of all the feasible tag installation options across different phases and gray out what is not feasible at other phases. Just ignore them. For example, if we build a wall at a certain phase, before that wall is not there, so we cannot place any tags on it. So we gray out that particular tag installation options for that wall. Elements in the array are whole numbers from 0 to the number of tag sizes. 0 means no tags, non-zero I means place a tag of size I at that particular location. The second requirement is defining a metric fitness score to compare the generated solutions. A fitness score consists of a utility and a cost component. The utility U maximizes localization quality and is a function of Fisher information matrix that is mapped to a scalar using a metric function, such as determinant, trace, and so on. The cost component penalizes adding extra tags or modifying the network throughout the project. This slide shows a sample project with 3 phases that we use to study the effectiveness of our cost function. On the left, you can see the 3D model and the plan view of phases with the ROIs hashed. On the right, you can see the UAV in the simulation environment, its camera image stream, and the detected tags. We found the optimal tag configuration for the 3 phases, with and without the cost function. With cost function, we can see the algorithm places tags such that they remain useful in other phases too. However, without the cost function, the algorithm finds an optimal configuration for each phase separately, resulting in high tag network modification. The results show that a proposed cost function could reduce the number of deployed tags by 57% throughout the project. Now let's focus on handling incomplete on-site data. Data is incomplete when it lacks essential elements or contains a high degree of missing values. On-site 3D point clouds can be affected by factors such as sensor limitations, occlusions, and reflective objects. This incompleteness leads to insufficient observability of elements and consequently inaccurate and partial element-wise quality assessments. Comparing elements in as-designed BIM with the registered 3D point cloud is a building block for project quality assessment as one of the major construction control processes. But independent analysis of elements can lead to inaccurate assessments because of the partial observability of elements. The hypothesis here is that we could use the semantic relationships between building elements to perform quality assessments under these conditions. For example, even if the wall in image D is not fully captured, observing the opening in it can imply that the container wall has been built and is not missing. This thesis proposes BIM-GNN, a novel approach to element-wise quality assessment that leverages semantics in as-designed BIM. It transforms BIM into a graph where building elements are nodes and their topological and spatial relationships are edges. We define the problem as classifying elements into 4 build quality status categories. Verified means element is built and matches the design. Deviated means element is built but doesn't match the design. Missing is when element is not built, and no data means there is insufficient information. BIM-GNN inputs as-designed BIM in IFC format, element-wise 3D point cloud correspondences, and a set of known labeled elements. It first transforms the BIM to a graph and then augments the graph with node features, edge attributes, and known labels. Node features include scan-based, graph-based, and beam-based features. Scan-based features include hand-engineered and learned features. Beam-based features include element type and floor, and graph-based features contain extra information about the graph structure, including node degrees, centrality, and so on. We also consider connection types as edge features. So we have a graph that we know the labels of some elements in it and want to predict the labels for unlabeled nodes in a semi-supervised transductive learning setting. This is to capture project-level context. We train our BeamGNN classifier on the same graph to classify the elements with unknown labels to our 4 build quality status categories. Our dataset contained 23 analyses from 5 different projects that were then converted to graphs. The figure on top right shows the distribution of ground truth labels for nodes in each graph, and we can observe an imbalanced label distribution across analyses. In our experiments, we used 10 randomized splits and started with splitting the nodes in each graph with 60% training, 20% validation, and 20% test, considering all the feature sets and edge attributes. We call this the original dataset. We compare results with a baseline model that we call ML Vanilla. ML Vanilla consists of an ensemble of supervised models with no semantic incorporation. It was trained on the scan-based features using tens of thousands of elements from various different projects. The table compares the performance of our model with the baseline model across all rounds, and figure on the right provides an overall comparison. The results suggest that our model outperforms the baseline significantly in all metrics and with an average weighted F1 score improvement of 27% with a lower performance variance. In another experiment, we performed a feature ablation study. The goal is to investigate the importance of the features by removing one feature or feature set at a time from the original dataset, including the whole scan-based features. Our results show that our model could still outperform the baseline even without the scan-based features, essentially with no on-site data. This is the case if we have access to 80% of the labels in each analysis, 60% for training and 20% for validation, on top of graph structure, edge attributes, and other 2 feature sets. This property of BeamGNN could be very useful when we are dealing with partially observed or unobserved elements. This thesis addresses 2 fundamental questions. First, how to enable autonomous low-cost image collection in indoor construction environments. Second, how to extract relevant information from incomplete on-site 3D point cloud data. In the first part, it introduced tag-based visual inertial localization to enable autonomous navigation of low-cost UAVs in indoor construction settings. Then it proposed a stochastic modeling of tag installation error to improve the robustness of tag-based localization. Finally, a 4D tag placement planning method was proposed to optimize manual tag installation efforts throughout the project. In the second part, it introduced BeamGNN, a semantic-aware quality assessment method to enable inference with incomplete data. This thesis had led to the publication of 7 papers, 3 journals, and 4 conferences. Our BeamGNN paper was selected as one of the top 3 papers submitted to ISARC 2023. In the end, I want to thank you all for your attention. Please feel free to reach out to me via email or using other platforms.